Okay, so we are going to carry on with our shear stress theory, and we are going to derive the shear stress equation, and I'd like to write the form of the shear stress equation. Okay, so based on this view, okay, and if you look at I'll write down the transformation. This is y, z, rotation, x, the shear stress equation. So if we look at 3D or what we are going to, so what we are trying to derive is, we know that over here, right, this is the x, the plane intersecting the x-axis, right? So this plane will intersect the x-axis, right? So what we're deriving is shear in the xy direction. So intersecting plane is x-axis, right? The plane will intersect x-axis. The shear stress will flow in a y direction, right? So this is equal to 3/2 Vy over Bc, right? And this is bracket 1 minus y squared over c squared. Okay. So this is based on the transformation that we see on the figure on the left hand side. So we're going to derive this expression over here. Okay. Now, it's important that we need to know how this equation has been formed. So I discovered this maybe 10 years ago. Okay, when I'm 40 years old. Okay, I'm 50 now. So 10 years ago, I discovered that it's important to know how this equation has been derived. Once you know how this equation has been derived, then you can set the rules. And these rules that I'm going to set, there are 5 rules. Okay, there are 5 rules that I'm going to set. These 5 rules will enable you to solve any problem from the first chapter, from the shear stress on problem 1 to the last problem. The rules always apply the same. Okay, and how I wish I discovered this when I'm at your age. I was ignorant. I did not. Okay, so I want you to learn early. Okay, so we are going to derive this equation. Okay, so we know, right, that the root form of this equation is shear xy. Okay, shear xy is equal to Vy over Izz Qz divided by T. Okay. So what we can see over here, Vy is coming from the vertical direction. Now, a lot of times students get confused is the Qz. Izz is simple, right? We do shearing stress. We know how to get Izz or how to get Iyy. That's easy. It's the Qz. So Qz is equal to a y bar. Okay, it's equal to a y bar. So Qz means, when you see Qz, what it means is the first moment of area about the z-axis, right? And the y bar is the centroid or the defined the distance between the centroid and the centroid of the defined area. Okay, so the defined area is the one shaded in the darker color. So not the area of interest. I would call this is the defined area. Okay, that is the, I can't write properly today. I think I'm too excited. Okay, so area. Okay, so area is the shaded region. Okay, y bar is the distance between the centroid. Okay, so between the centroid, so this is the centroid. I'm going to sketch in dark green. I'm going to sketch in dark green. So this is a centroid. Okay, so this is our centroid. And where y is, okay, or where c prime is, the dot is, okay. So I'm going to draw a line, also a lighter green. Okay, so this is the centroid of the defined area. Okay, so from here we set rule number one. Okay, rule number one. Okay, rule number one. I'm going to write out rule number one first. Okay, so rule number one is the shear force V and IZZ are constant regardless of the position or regardless of the defined area. Okay, so that's rule number one. Okay, what it means is that V, okay, V over here, or Vy, sorry, and IZ. So Vy, okay, Vy and IZZ are constant. Okay, are constant regardless of the y distance. Sorry, the y bar distance. Okay, are constants regardless of the y bar distance. Okay, so the only thing that change, okay, there are two things that change. The only two things that change are your QZ and T are not constant. It's dependent on where your y bar were interested. If you realize now, okay, there's only one equation that we use that now when we come to this course, there's only one formula we use that calculate the average, which is stress X is equal to P divided by A, right? From bending moment onwards to the shear stress onwards, we are not calculating the average anymore, right? We are calculating the distribution. You realize that, right? We are calculating the distribution. Okay, later on I'll show you the distribution of the shear stress. Okay, now coming back to here. Okay, so you know that QZ is equal to AY bar, right? And an important thing to take note, okay, is the first moment of area is about the z-axis. Okay, now I'm going to do something slightly different. Okay, I want you to look at another orientation. What if now, okay, we are going to do this? Anyone put up hand yet? Not yet. Okay, what if now this is our member, our cross section again, right? Now the shear force is in this direction. So this direction is your VZ. Okay. So now the centroid is from here now. Okay. So now the centroid, or now the axis is acting on is on your what? YY. Right. So that is why now the formula. Okay. So now we have to know. Hey, Eugene, if this is the case, what is the shear we are looking at? So we are looking at the shear stress. Okay. Shear stress now is in the intersecting plane is still X, okay, because the transformation is still the same. This is your Y, this is your Z, this is rotation about the X, okay. So the plane of the plane that's intersecting the X which axis is the X axis. Now the direction is Z. So this will be equal to VZ over IYY, okay, QY divided by T. Okay. Now, what do we mean by QY now? Okay. Now the thing is, what do we mean by Q? So QY is equal to A Z bar. Okay. So QY is defined as the first moment of area about the y-axis. Okay, about the y-axis. So how is this measured? Okay, so I'm going to zoom in now. So let's say now this is the area of interest. Okay, this is the area of interest. And a point down here, which is known as C, it is the centroid of the area of interest. Okay, so this is your Y bar. Sorry, this is your line where you're interested. Hold on, I'm just drawing a straight line. Pardon me. Okay, right. So this distance from here, from the centroid to here, let me change color. From the centroid to here, this is now your Z bar. Okay. Now coming back to our previous diagram, okay, this over here from the what? From the centroid, okay, to the defined area centroid, this is our Y bar. Okay. So from here, I'm going to write rule number 2. Okay, rule number 2 state that the rule number 2 state that the datum is at the centroid. Is at the centroid. Global centroid. Okay, global means the entire structure. Okay, it's at the global centroid. Okay, rule number 2. Okay, so now we are going to now find our first moment of area. Okay, so we are going to focus the diagram on the left. Okay, so I'm going to copy this whole diagram. Okay, so Y bar or Q, yeah, or QZ is equal to A Y bar. Okay, so to find the cross-sectional area, the constant is the width, and then the depth. Okay, so the depth is your sorry, what am I talking? So so if we want to look for the area first, okay, we want to look for the area. Okay, area, the width is B, the depth is C minus Y. Okay, the Y is this Y over here. Now this equation, yeah, is c minus y. Any idea why it's not y minus c? Anyone? Why is it c minus y? I got no answer.
Because of what we just said, that the datum is at the global centroid.
It's not y minus c, right? It's purely for one reason. You will get a negative value. It has to be c minus y is positive. And when they write c minus y is positive in that sense, okay, we can state another rule. Okay, so rule number 3 is that the analysis starts from furthest or from distance